get started. Let's dive back in. Here's where we were. We were talking about this geometric properties of a list of vectors, and I guess we started by looking at a pair of vectors in 2 dimensions. And when you have a pair of vectors, like so, for example, the idea is that once you make a list that establishes which one is first, which one is second, then that allows you to decide, in most cases, generically, the list is either clockwise or counterclockwise, right? Okay, so I claim that there is an analogous thing in 3 dimensions, and we got to talking about what that is, but I didn't get to describing in what ways is it analogous. Right, so here's where we were. We had this idea of right-handed and left-handed, and so a list ABC is either right-handed or left-handed based on. And remember, we had this kind of hand gesture thing, right? This is the hand gesture like this: index parallel to the palm, middle fingers bending the way middle fingers want to bend, thumbs pointing on one side, as indicated by which hand you're talking about, one side of the plane defined by the first 2 dimensions. Okay, so we talked through a couple of examples. Okay, so why is this like clockwise, counterclockwise, you ask? Well, just like clockwise, counterclockwise, they're mirror images of each other. Right? And I think that's a pretty easy pitch, right? You look at my right and left hands, they're clearly mirror images of each other. If you switch the positions of 2 of the vectors in your list, that switches the handedness. Right? And all of this is independent of rotations. So all of this, I think, is pretty geometrically satisfying. This one here, the order is independent of the rotation. Well, if what I have here, if this hand gesture that I'm doing with my right hand right now represents 3 vectors A, B, C, if I were to rotate all 3 vectors in the same way, I can still do it with my right hand, right? So completely independent of rotations. All right. So notice that's the same 3 first properties that we talked about with clockwise, counterclockwise. They're mirror images of each other. Trading the positions of 2 vectors, well, there only were 2 vectors, but anyway, trading the positions of 2 vectors changes the order, and it's independent of rotations. So this is a very close mimic, you might say, of clockwise, counterclockwise, but for 3 vectors in 3 dimensions. Now, there is a 4th property, or kind of isn't, well, it depends on how you look at it. I'm going to say there sort of morally isn't a version of this in 2 dimensions, but what I'm going to call cycling the vectors in the lists preserves the order. This is arguably a special case of the previous property. But if you take the 3rd vector and put it in the 2nd position, you take the 2nd vector and put it in the 1st position, you take the 1st vector and bring it back around and make it the 3rd vector, like so, that doesn't change the handedness. Right? And for whatever it's worth, here's a hand gesture. I'm going to try to do this without making a rude gesture to the audience. This is a list, right? So remember 1, 2, 3. And now look at this move here. Right? See what I'm doing with my hand here? Just kind of twisting my hand. When I do it like this, it's pointing in the same 3 directions, but the ordering of those 3 vectors has been cycled. And all it is, you'll notice, is basically kind of rotating my hand again. And so again, that preserves order. Okay. All right. So these ideas of clockwise, counterclockwise, and right hand, left hand are going to show up unexpectedly but powerfully in the next couple of theorems that I'm going to mention. These theorems, now, it's possible you might have seen these in your linear algebra class. It depends on which linear algebra class you took. There are 3 different linear algebra classes that feed into this course, so who knows. Anyway, if you haven't seen them, no problem. Here we go. Now, there is a fair amount of setup for this theorem. So you're going to have to be patient with me. I'm going to talk through all of the setup to make sure we know what are the players in the story that I'm about to tell. And all of what we have, on the screen here is just setup. This isn't really even the theorem yet, right? You can see here's the then, that's the start of the conclusion is all the way down there. So all of this is just set up, and here we go. We start with a list of vectors. That's a pair of vectors, but with an indication of which one's first, which one's second. Well, if you have a list of vectors, that allows you to make a matrix. Whichever is the first vector, make that the first column. Whichever is the second vector, make that the second column. Now we have both a list and a matrix. Okay. Well, here's the thing. If you have a matrix, that allows you to define a linear transformation in what I'll call the usual way. Right? This is how we turn a matrix into a linear transformation. Said differently, this is how we represent a linear transformation with a matrix. Okay. And when you have a linear transformation, that allows you to define a parallelogram. And I'm going to say in a sort of a standard way, the idea is we're going to consider the unit square here as kind of the world's easiest, world's simplest parallelogram, arguably. Right? And so if you look at that unit square and plug it into this linear transformation you've got, then out comes a parallelogram. Okay, all right, so these are the players in the story. And now let's start talking about what the theorem actually says. The first part of the theorem tells you, by the way, this theorem's about determinant. Determinant is our subject here. The determinant of this matrix, of course, its absolute value gives you this area. So that's the first part of the conclusion. I think this is a really surprising result. Determinant is defined algebraically. It's a formula. It's not even a complicated formula, right? It's three-function arithmetic. Multiply, add, subtract. Right? Pretty simple arithmetic. And yet the answer is the area of a parallelogram that has some weird angle at the origin there. And you would think that trig would get involved. By the way, the lengths of the two vectors involve square roots. How are we computing that area with three-function arithmetic? Where's the square roots? Where's the trig? I find it very surprising. Okay, but it's true. The second part is a little harder to talk about. It concerns, again, the determinant. This time not the magnitude of the determinant, but the sign of the determinant, whether the determinant's positive or negative. And those two possibilities refer to, I'm going to go ahead and zoom out a little bit so we can fit more of this on the screen. Those two possibilities, positive or negative, manifest in some interesting ways. All right, so first, sort of the easy version of the story. If the determinant is positive, then the original list, keep in mind we started off with a list counterclockwise. And that's how I have it drawn here in the picture. You can see A to B counterclockwise. All right, so the picture as I have it drawn here is of a positive determinant. Okay, now let's talk about a negative determinant. What would that look like? And I'm going to have to adjust my picture. My picture doesn't work. I'm going to scratch that out and that out. So the negative determinant would look like if, I'll go ahead and make this purple. If A were that vector and B were that vector. In particular, then, that means that AB is clockwise. So this is what the picture would look like if the determinant were negative. I think this is pretty weird. I mean, the determinant, again, is defined algebraically, simple algebraic formula, and yet it's right on this kind of spooky, even geometric concept of, we're talking right hand, clockwise or counterclockwise, which way does it go? doesn't seem like that would be so algebraically just trivial. Okay, but neat fact. Okay, now there's another take on this, another way to think of this conclusion, and that is in terms of what the linear transformation itself does. And the linear transformation itself, I can also draw a conclusion from determinant being negative. I'm going to try to represent this with a little bit of colors. The big idea is to observe that E1 has as its image, remember our big theorem from last time or the time before, was that the image of the standard basis vectors are the columns. So the first standard basis vector, its image is the first column, which by design is A, the first vector. And likewise, the second standard basis vector, its image is the second column, that is this second listed vector B. And so notice what's happened. A counterclockwise list has as its images a clockwise list. And let's just think about this geometrically for a moment. What can you do? I mean, what sort of like geometrically, physically, if you want to think of it that way, can we do with a linear transformation to make a counterclockwise turn into a clockwise? And there's a bunch of different ways to say it. I think a pretty reasonable take is that you're flipping it upside down. Right? If you want to turn a counterclockwise rotation clockwise, doing it upside down. So somehow, depending on how you want to think about it, when the determinant is negative, various other results, of course, but there is a flip or a reflection or a turning over, say it however you want to like. I use the term here inversion. Right? Somehow or another, that linear transformation flips things upside down, inverts, however you want to say it. Okay. All right. And that's if the determinant's negative, and as we've written up here, and let me go back to the original drawing. When the determinant is positive, then counterclockwise just goes to counterclockwise, and there is no flipping because we're keeping the order the same. Okay. All right. So neat fact. We're not going to prove this theorem, by the way. Not that we couldn't, but I don't think it's a good investment of time, and I don't think you need to be bothered by it. I think this is a good take my word for it result. And if you're curious, I believe this is proved in the book. So you can read that proof if you're interested, but it's not going to be part of the course. Okay. All right. Next, in 3 dimensions. Very similar theorem. Shockingly similar theorems. And I think excellent argument to support the claim I already made that right-handed, left-handed really is kind of a 3-dimensional version of clockwise, counterclockwise. Because, and by the way, I've written this out on the page deliberately to mimic the layout of the 2-dimensional theorem. I tried to keep it as close as I could. Very, very similar layout because they are very, very similar theorems. Now we have 3 vectors in a list that, by the way, of 3-dimensional vectors. That makes then a 3 by 3 matrix, which in the usual way makes a R3 to R3 linear transformation, which produces a, well, I guess you'd say a 3-dimensional version of a parallelogram. We call that a parallelepiped. It's just kind of a 3-dimensional version of what we saw previously. And the analogous results hold. The magnitude, absolute value of the determinant, gives you the volume. Now, it's not area. It gives you volume now. Well, of course, because the size of a 3-dimensional thing is not described by a 2-dimensional quantity, right? We use area as a 2-dimensional quantity to understand how big 2-dimensional things are. We use volume as a 3-dimensional quantity to understand how big 3-dimensional things are. So this is the analogous claim, the volume of that parallelepiped. And then again, the sign of that determinant, positive or negative, or there's also the anomalous, the weirdo case of the 0. But let's just talk about positive and negative. It tells you whether the resulting trio of vectors, the resulting list of vectors, is right-hand order or left-hand order. And analogously, because of course E1, E2, E3 are always right-hand order, if this became left-hand order, again, think it through. What can you possibly do to turn a right-hand list into a left-hand list? Can I do this by kind of rotating? Can I rotate my right hand around to look like my... no, it just doesn't work, right? And you can think of all sorts of magnifications and stretches and shearing transformations, etc. None of that will do it. Only reflections. Which, by the way, you can think of as flipping upside down through the fourth dimension. That's a creepy thought. You don't have to think of it that way. It's not that different. So, reflections are what it would take to do that, namely some sort of an inversion that reverses the orders. Okay, so totally analogous result here, so this business about right-hand order, left-hand order, playing the role of clockwise, counterclockwise. I think you can see the strength of the analogy. How we doing? Everybody with me? Okay. All right, so we're not going to prove this theorem either. This theorem is, again, it's a bunch of details. And by the way, the best way to prove this theorem, in my opinion, is to use some, I'm going to say, kind of sophisticated linear algebra. This isn't a linear algebra class, and we don't have the time, etc. Again, if you want to see a suboptimal proof, you can look in the book, something like that. But there is a much better proof out there, so I don't even particularly recommend it. Okay, so here we go. Moving along. We'll talk about cross product. Here's our definition of the cross product of two vectors. Cross product A cross B. Some of your linear algebra classes have talked about this already. If not, here's the formula. It's just a formula. Now, reasonable question, why would we ever be interested in such a thing? And it turns out that this formula has some really strong connections to ideas we've just gotten through talking about. I'm going to work my way into those. It'll take us a bit to do it. First, I'm going to start by recognizing that you don't need to memorize this formula. There's a much easier equivalent formula to memorize. It's this, what I call symbolic determinant. I feel the need to kind of asterisk calling this a determinant, because a determinant is something we do to a matrix. A matrix is supposed to have entries that are elements. This has entries, some of which are vectors. That should strike you as weird. It's not really quite, is it really a matrix? Is that legal? Can you do that? It's a legitimate concern. Right? But anyway, I'm just going to call it a symbolic determinant. Namely, start writing down just determinant like you normally would, ignoring the fact that some of those things aren't scalars. Just write it down, and what you write down is a formula that we'll call the symbolic determinant, and it turns out to be the same as the cross product. So, in my life, I've never memorized the formula on the left. I am quite sure that if I tried to memorize that formula on the left, I would misremember it at some point. I would forget a minus sign, or I'd get I'd get those two products in the wrong order in one coordinate or another. It'd be really easy to mess that up. But this formula here, I think, is pretty easy to memorize. It's got a nice, simple pattern. E1, E2, E3. First vector there. Second vector there. Pretty easy. Everybody with me? Okay. All right. So now here is a slick move. Very slick move. If you take the cross product, there it is. Now that's just recopying the formula from above. If you do its dot product with some other vector, dot product, the dot product with a cross product is exactly that right there. And again, nice, simple, easy to remember little formula. It's sort of eyebrow raising that it's so simple to write down. First vector, first row. Second vector, second row. Third vector, third row. So determinant being well established, important, significant, useful construction. That makes this highly suspicious that that's probably going to be some sort of a useful thing. So this is what we call a triple product, and very closely connected to dot product and cross product. That's the formula. Very closely connected to determinant by way of this little algebraic observation. And again, you just got to look at it and go, oh my God, son of God, there it is. It's exactly the determinant, right? There's a lot of benefit that you can get out of this formula. And let's see, let me highlight. Because of this formula and because we already understand determinant and we already understand dot product, knowing that these two expressions are the same allows us to make connections to what we're trying to understand, namely this new construction called cross product. So that's going to be our foot in the door, as it were. Yeah.
If the order was flipped, would the
yeah, you got to be careful. It is true that C and AB. Yeah. If you do this, dot product is perfectly happy with that. Yeah. Right? In some sense, you're not doing anything when you do this, but you are changing the order of those three vectors. And so that's changing, if you look at per this equation, that's changing the order of the vectors in the matrix. And then there's some questions as to whether, wait a minute, is that okay? And yes, it is, as it turns out. But it just brings up a lot of questions, right? So my advice is just, there's no reason to flirt with problems. Right? I think this is kind of flirting with problems. So I would encourage you to always write your triple products as such, right? So the dot product on the left, the cross product on the right. And then you don't have to worry about an uptight grader who questions whether the theorem you wrote down technically follows because you changed the order or something like that. Does that make sense? Yeah. Yeah. Okay, good deal. Alrighty, so bad news, good news. The proofs of the various results that are about to follow are optional. You don't have to read them if you don't want to. They're not officially part of the course. That said, there are a lot of really great ideas in these proofs. I leave them in here because I think you would find them instructive. I think it's good mathematical weightlifting. Another one of my favorite metaphors. If you lift weights, the weight was on the ground, you pick it up, you do stuff, you put it right back on the ground, and right where it had been, you didn't accomplish a thing, so it seems. But it makes you stronger. Right? So I think the same is true of a proof like this, from a strategic point of view, right, in terms of the course. Does this actually, do you have to know this? No, you don't have to, but it will make you a better mathematician. It will give you better practice thinking about the ideas that we've been talking about. I think this is fantastic mathematical weightlifting. Again, optional, you don't have to do it, but I encourage it. What you do have to know are the theorems themselves. So this, of course, not optional. This is something you do have to know. This is the first big result. Cross products are always orthogonal to both of the input vectors. Very important property of cross product. Now again, you can look at the proof if you like. You don't have to. It's not a hard proof. In fact, there's arguably two proofs here. But anyway, true fact, very useful fact. Okay, triple products have a weird kind of symmetry of sorts about them, and that is that you can cycle the vectors in that sort of list, if you will, and the cycling doesn't change the value of the triple product. Now, is that kind of familiar? Yeah, it probably kind of is, right? And this isn't hard to prove. And again, there's the proof. I encourage you to read it. You don't have to. But neat result. And make sure that you remember this result. By the way, notice cycling only, right? This does not change the order of the vectors however you like. There are 6 different ways to order 3 vectors. I'm only saying these 3 are the same. The other 3 are not the same as these 3. Okay. All righty. Let's see here. Here's a weird one. If you look at the cross product of a pair of vectors and look at the magnitude of that cross product versus if you look at the parallelogram. By the way, this notation right here, I probably subconsciously borrowed this from some other context, but I don't remember, so it's possible also that I made this up. I don't know. Anyway, 2 parallel lines followed by a pair of vectors. To me, that denotes the parallelogram represented by those 2 vectors. I'm going to use that notation. I think it's really convenient. That parallelogram, you can talk about its area. And I'm going to say kind of shocking claim is that the magnitude of the cross product and the area of that parallelogram are always the same. Very weird, right? Very kind of spooky. Now, lovely proof. I love this proof. It's awesome. Very clever proof. Don't think to yourself, oh, sure, I totally would have thought of that. This is a very clever proof. Don't get intimidated by this. Now, again, you don't have to look at this proof, right? All these proofs so labeled are optional. But I do think it's a neato proof. And this first move of considering this determinant comes out of nowhere. It's not something you should naturally have thought of yourself. It's just super duper clever. Okay. All right. A neat analogy between cross products and dot products. So y'all remember there's a theorem that says that if a dot product is 0, then you draw a conclusion about the vectors. Namely, the vectors have this geometric feature of being, either one of the other vectors is 0, or they're perpendicular, right? Strong connection between dot product being 0 and perpendicular. This theorem says that if the cross product is 0, then they're possibly one of the vectors is 0. That's a little annoying. But parallel basically is the strong connection here. Those 2 vectors have to point in the same direction, again, or one of the other vectors is 0. So very analogous to a familiar result about dot products. Let's see here. Again, cool proof. You don't have to. Good mathematical weightlifting. Here's a nice one. This list is never in left-hand order. Ever. The sloppy way to say this is that list is always in right-hand order. That's technically not quite true. A or B could be 0. The cross product could be 0 if A and B are pointing in the same direction. So it could be that list is neither right nor left-handed. Sure. But other than that, it's always in right-hand order. So neat fact to remember. Another way to say this is that if you want to know which direction the cross product points, the right-hand rule is basically just this theorem in disguise. The right-hand rule says index finger in the direction of the first vector, middle finger in the direction of the second vector, your thumb will point in the direction of the cross product. Basically same statement. Okay. All right, again, cool proof. So for whatever it's worth, here's an arbitrary, here is an alternative description of the cross product. Now you remember the cross product I defined with a formula, and then I proved that it had various geometric properties, including these. The book uses this list of 3 properties as a definition, and then in some sense kind of turns all the reasoning around backwards to derive the formula. Now there's pros and cons to these 2 different takes, right? What the book does is very reasonable mathematically, right? But it has some downsides. I think it's harder to follow. I think it's less geometrically satisfying. That's just my opinion. So anyway, but I did want to present that as something to think about. Whether you call it a definition or not, this certainly is a purely geometric description of the cross product. It's the unique vector that's perpendicular to A and B with magnitude given by the area and that satisfies a right-hand rule. And there will always be exactly one vector that satisfies these 3 properties. It will always be the cross product. So, okay. A couple more quickies. Cross product does have some nice algebraic properties. Again, you've probably seen some of these in linear algebra classes. You may have. I won't assume. But it's not commutative. When you switch the 2 vectors in the cross product, you don't get the same thing. That's the bad news. The good news is you do get something predictable. Switching the order always exactly gives you a minus sign. So there's a neat feature there, something to make sure to keep in mind. Don't play too fast and loose with the algebra when you're doing cross products. Got to watch out for stuff like this. A lot of people forget that minus sign by just being a little too careless with algebra. Yeah.
Look at the 2 bars on the left side. It says area.
Oh, yeah, this is that notation again. This is the notation that I use for a parallelogram. Parallelogram defined by those 2 vectors. Yeah. Cool. All right, a couple other facts. Now, this was a kind of a homework exercise. I'm sure y'all remember that we, in one of the AHPs, I asked y'all to show that this linear transformation has the feature, that this function is a linear transformation, that it has the feature of being linear. And just to be explicit about what that means, remember T means A cross. So that's T right there, and there, and there. So if you just replace each of these with a T, I think you can see that is pretty much just the definition of linearity. Right? So algebraically, as an algebraic property, it's almost like there's sort of a distributivity and associativity, sort of scalar associativity that applies to cross product. So anyway, ultimately just a statement about linearity. And then likewise, if you do it in the other order, if you put the cross A on the other side, what it looks like algebraically changes a little bit, but it's basically the same idea. Okay. And do be careful as well. Cross product, while it does have a sort of a scalar associativity, it is not vector associative. And this is easy to disprove. In fact, if you were to write down 3 random vectors, A, B, C, pretty strong odds, these 2 simply won't be the same. Yeah?
How does the proof above prove that it is linear? Like, what about it?
Oh, yeah, so the definition of linear is that, you put a linear combination in, you get a linear combination out. And, taking the point of view that this is what T is, you can see here we're putting a linear combination into the function, and then here we're getting a linear combination of otherwise outputs from the function. So yeah, it's just what the definition of linearity looks like in the context of that function. Yeah. All right. Okay. Okay, a couple of quick applications just to show you that this does come up and does have uses if you're a mechanical engineering major. Torque, it's kind of a big deal, right? Useful concept. Fundamental player in the story of mechanics, right? This idea of torque. It's kind of like an angular version of force, in a way, depending on how you think about it. If you have some axle like this, and if you have let's say, I like to think of this as being like a wrench, right? And you're pushing up on the wrench with some force like that, then the cross product there of the wrench arm and the force describes this thing called the torque, and again, fundamental player in mechanics. Okay, so that is a cross product. So again, this is physically, in the real physical world, naturally arises. Here's another such example, and that is if you have a charged particle moving through a magnetic field. So this is kind of a weird one. In some sense, everything about magnetic fields is weird. I don't know how much y'all have seen about magnetic fields. There's a lot of weird stuff there. But if you have a magnetic field pointing like so, and if you have a particle moving through the magnetic field, a charged particle moving with a velocity like that. So let's see here. So the magnetic field is that way, and then the velocity is that way. The cross product, velocity cross magnetic field, that cross product gives you the force. There is a resulting force produced by the movement of the charged particle through the magnetic field. And again, computed with cross product. Real world manifestation of this construction. Alrighty. Okay, so now another thing, I want you all to take a look at this. This is something that can be used. It has some nice notational advantages that come up in a few places. So we will be making references to this later in the course. I'm not sure how standard this notation is. I don't recall seeing it in my own physics classes when I was in college. So anyway, you may have a different experience. I don't know. Anyway, still useful. It's called the two-dimensional wedge product. So this is an operation in 2 dimensions. Oh, by the way, there's a PDF file that I've put in the course materials folder, along with a bunch of other PDF files that Professor Aspinwall produced for his sections, but he's kind enough to let us all have reference to them. Wedge2.pdf. So if you want to see more details about this, you can find that in the course materials section. And the big idea is it's computed by this formula. The wedge of two-dimensional vectors is the determinant of the 2x2 matrix produced by those two vectors. And you see I've written these here horizontally. It could be vertically. It doesn't matter. Okay. We'll shoot. What's the difference then between a wedge and a determinant? How are these different at all? And, well, the big difference is determinant acts on a matrix. Right? A matrix is an algebraically defined thing. Wedge product does not act on a matrix. Wedge product acts on a pair of vectors. And please don't conflate a pair of vectors with a matrix. They're not the same thing. Yes, of course, if you have the one, you can produce the other in a sort of simple way, right? But it does remain that they are different things. Anyway, just please be careful about that. So why do we care about the wedge product? Well, it's kind of ripoff of the idea of a triple product in these ways. And you can flip back through the notes and see that these are features of the triple product that we talked about. It's also kind of like sort of a, if you will, kind of two-dimensional version of the cross product in some ways, such as this. And again, flip back through the notes, persuade yourself that we've kind of talked about these things. And I will note real quick, this is the area of the parallelogram. I didn't write that formula down but it's in the book. That's the magnitude is the area sort of thing. Okay. All right. So details for y'all to read, but again, this is going to pay off with some notational conveniences when we get to the end of the course. Okay. All right. Moving along. So equations of planes. I think a lot of y'all have seen equations of planes in linear algebra classes. Again, I know y'all have had different linear algebra classes, so some of y'all might not have. To the extent that you haven't seen this before, this is kind of borderline on the tough choices scale, right? Whether this is, keep in mind every minute we spend talking about stuff here is a minute that we can't be spending talking about the much more sophisticated ideas in chapters 6 and 7, and 5's no joke as well. So there's a lot of much more sort of deserving, I think, material later on. So I am going to move kind of quickly through a lot of this stuff, but I do want to hit the highlights. And so let's talk about a plane, and how would I write the equation of that plane? Now we do have to say which plane. I can't just say, hey, I'm thinking of a plane. You have no idea what plane I'm talking about, right? So I'm going to need to specify a point in the plane and a vector perpendicular to the plane. And if I were to specify those, then there is, of course, only one plane that I could possibly. There's always a unique plane, right? That's perpendicular to the given non-zero normal vector and that contains a given point. Okay. All right. So how do we find the equation of this plane? Well, the big idea is that keep in mind an equation is a test, and the test, pretty straightforward, is that this difference vector. Think about it. R0 is given to be in the plane. I want to entertain what would happen if this other vector R is also in the plane. If I have two vectors in the plane, their difference is parallel to the plane, which means that that difference is also perpendicular to that given normal vector. And perpendicular, okay, well, there's the whole orthogonal perpendicular thing. But dot product is equal to 0. And by the way, we can arbitrate the question here of, do I want to consider, what if this were the 0 vector? Should that be included? Well, if that were the 0 vector, I would literally be talking about the point R0, which, yes, is in the plane, and I do want that to count. So orthogonal, not perpendicular. Orthogonal is what we need here. Kind of convenient. Right? We're making kind of a geometric argument, but the geometric notion of perpendicular doesn't fit as well as the algebraic notion of orthogonal. So I think it's kind of wild. Okay. All righty. So this is the equation of the plane. I very often like to rewrite like so. It's morally the same equation. I find that it just rolls off the tongue a little bit more easily in this form right here. And if you make the choice, reasonable choice, if you choose to represent the normal vector by coordinates A, B, C, and keep in mind that R is our X, Y, Z, then that dot product in dot R expands like that. Everybody happy? Okay, so a different way to think about the same thing morally. So you can think about this as the equation of the plane, or you can think about this as the equation of the plane. Now let's again talk about pros and cons. Sometimes what you want in the equation of a plane is algebra, scalar algebra, such as the bottom of those two equations. Yeah, sure, true. Sometimes, though, what you want is an equation where the relevant players, right, the significant, the mathematically meaningful objects are visible in your equation. That's a good thing, right? So the top equation is actually my personal favorite. I think that is the one that most naturally connects the idea of what the equation of the plane is with why that's the equation of the plane. So don't make the mistake of always rewriting everything in terms of coordinates. That's a definite mistake. Vectors are good things. There are ideas there. That's the foothold into geometry, and geometry is a good thing. Right? So anyway, don't be too quick to convert to coordinates. Okay, let's see here. Suppose we're given a trio of points. How would I find the equation of the plane that contains those 3 points? Well, if you want the equation of the plane, we'd go back up here, see what it is. And the equation of the plane, you can see I'm going to need a point in the plane. Do I have a point in the plane? How am I going to find a point in the plane? Well, I have 3 of them. Take your pick. It doesn't matter. I'll pick A. It doesn't matter. Anyone will do. Okay, what else do I need? I'm also going to need a normal vector. I'm going to need an N. I'm going to need a vector perpendicular to the plane. How am I going to produce a vector perpendicular to the plane? Here's the trick. The trick is that I can take these purple points and subtract one from the other 2 to get vectors parallel to the plane, and given vectors parallel to the plane, the cross product will produce a result perpendicular to both of those vectors and therefore perpendicular to the plane. So, slick little move there, right? And again, I didn't think of this. Somebody showed me this many, many, many years ago, and now I'm showing you. And so, anyway, don't ask yourself whether you would have thought of this on your own. Note that you've already seen the trick, and so you just have to remember what the trick is. Okay, how are we doing? Everybody on board? Okay. All right, I'm going to end with a clever little observation. I like to use this in various places in the course. I don't remember if this is in the book. I kind of don't think it is, but there's a real neat, that's very clever, very useful. If you're looking at the equation of a plane and there are no y's in the equation, like so, the coefficient of y is 0. Based only on that, we can conclude a very useful geometric conclusion, and that is that plane is parallel to the y-axis. And I love it when stuff like this happens. Something that you can eyeball notice at a glance, and then you get a powerful geometric conclusion. Right? It's totally awesome. It's pretty easy to see why this is. No big deal. After all, we know that these coefficients tell me the normal vector, right? And I know that the plane is perpendicular to the normal vector. Well, I can do a simple dot product that shows me that the normal vector is perpendicular to the y-axis. And if the plane's perpendicular to the normal, and if the normal is perpendicular to the y-axis, you got to think about the geometry there. But the conclusion that we want follows immediately from that geometry, that the plane is, and I've done my best to draw it representative, the plane has to then be parallel to the y-axis. So neat conclusion. So be on the lookout for these opportunities. They come up from time to time. They will definitely come up in this course. And yeah, so just look for missing variables. Y'all have a good rest of your Monday. See you later.